Okay, I would suggest we just start. So good evening now to the security part again of the session. What we have now is Dan from the Cambridge University, the computer lab there, who did a rather practical approach to the wireless sensory networks, especially mica or ZigBee. So give me your hands, please, for Dan.
Thank you. Thank you very much. I'm going to talk about some of the results of a project I've been working on in 2007 mostly. And the main goal of the project was to deploy some wireless networks to monitor large civil structures like bridges, London Underground. Down? No problem. What we are trying to do, our plan was to work indoor when it was raining and outdoor when it was raining. More specifically, we wanted to develop systems for monitoring large civil structures, as I mentioned just now. We wanted to use off-the-shelf products because the project had some sort of limited budget, so we didn't want to build our own systems. We wanted to interview owners or operators of the bridges and, let's say, underground Thames Water, who are running water pipes in London. And also we wanted to do some hacking of systems, of wireless solutions we can buy. We had some sort of expectations about security, and those remained basic expectations. So what we've been using, we bought several sets of mica Z modes. I don't know, you may know them. You can buy them from Crossbow Company, which seems to be market leader in, let's say, sense networks today. So they can really send you kits you can start using and play, messing around, measure environment, temperature, humidity, stuff like that. Those modes don't connect directly to the internet, so if you want to connect to backend computer, you need some sort of gateway, which was in our case Targate, which is embedded Linux box with a connector into which you can plug one of those mica modes. Some USB programmers, hardware debugger that was invaluable, and VMware and several Linux Win boxes. Most results I will be talking about are applicable to Iris, T-Mode, Intel Mode 2 devices as well, because they use the same radio, pretty much the same software as well. Talking about software, the basic software for the modes is TinyOS. It's a GNU project that was initiated in Berkeley in California, and you can download it, you can compile, and you can upload your software to the modes and run your own applications. As I mentioned, the main goal was to deploy the networks into real environment. So not to use it in a lab on your desk, but to go to tunnel, deploy the mode there, and measure something useful. And because the project was run by engineers, they wanted to measure structural properties of tunnels or bridges. In that case, you need basically three-tier topology. There is backend system with the database and all analyzes, whatever analytics software you may need, which was on a server at Cambridge. Then in the middle, you got gateway. That was the Stargate, embedded Linux box, and that one is talking to the backend via internet and the Ethernet connection you can get through ADSL if you're really, really lucky, or GPRS if you're not so lucky, or you may need to use several hundred meters of cable to get somewhere where you can get at least the GPRS. So the gateway connects to the wireless network itself via serial port and basically ZigBee, which is 802.15.4 IEEE standard. The actual hardware components we're using, as I said, Crossbow, Stargate, mica Z modes, and TinyOS 1.1 or Xmesh, which is basically version of TinyOS software licensed by Crossbow, so you have to pay for it, and part of it is not is being sold only as in compiled libraries. So at the beginning, there were two myths we had. One was about smart dust, and the other one was about security. I will talk about security most of the time. So the smart dust myth, you may have seen pictures like this, very small sensor size, a couple of millimeters, and it is, I don't know, powered by solar energy. It can measure environmental properties like temperature, humidity, and it will be able to talk to other modes and send some useful data to your backend system. Well, what you could have bought a few years back is this, which is mica dot, the size of, let's say, euro coin, but it's not being produced anymore. It was discontinued. So you can buy this, which is the mica or mica Z we've been messing around with. The size is 2 AA batteries, because the batteries are behind that PCB. Or if you're really serious about measuring anything practical, you will end up with something like this. And the mica Z is somewhere in here. This is double-D battery, so you get at least a year or a couple of years of lifetime. Only the battery will cost you about $80 or $50 on the internet. And of course, you will need some serious sensors. We've got inclinometers here and some external temperature sensors. So the myth of something small that you can just throw around and it will work is really just a myth. So there's another example of a sensor we created or built, and we put it to, this is, I believe, from London or Prague Metro. So we started with, well, several things, but I will start talking about what the civil structure operators think about security. There are 3 security properties: confidentiality, integrity, and availability, or availability. So confidentiality, well, it wasn't really issue because really the data you're getting from sensors is low level. So no one is really interested in protecting, securing this sort of data. Bridge or underground operators were a bit more careful in case you can aggregate the data and you will get something more interesting, like, yeah, we've got a piece of tunnel somewhere collapsing, then they would like to hear about it before Daily Mail or other journalists. So our result is do not rule encryption out, but do not stick it in by default. So you should always think about what sort of security properties I need and what sort of mechanisms I need, because every extra mechanisms you implement increases complexity of the whole system. Availability wasn't really that much critical, and we are a bit surprised by that, but it will change once you start thinking about networks or systems that have got some sort of actuators or real-time or requiring or are based for real-time response. What struck us during the interviews was that the managers were not really much imaginative and didn't really predict any future applications. But when we put a question like, do you think that once you got an infrastructure in place, is it going to be overloaded with new and new applications? They said, yes, it happens all the time. So yeah, you can create some or do some sort of security analysis or risk assessment for the solution you're building, but it doesn't mean that the assumptions you make at the beginning that the infrastructure will be used only for certain type of things will hold forever. So integrity is a bit more tricky. Basically, we found three types of integrity: short-term, medium, and long-term. When long-term, we're talking about up to 100 years. The bridge or the underground tunnels are 120 plus years old. The bridge we were working on was 50 or 60 years old, and there was another 30, 40 years of lifetime ahead. So if you're talking about long-term integrity, you need to think about really long-term. What were computers 40 years ago, and what will be computers 40 years from now, for example. So short-term integrity, false negatives, meaning bridge is collapsing, but the network will not say a word. It's very hard to explain if there are not that many events, and bridge collapsing doesn't happen every day. It happened last year in the US, Minnesota, I believe, and not a few years back in Singapore, somewhere there. But there are not many instances of such events. False positives are more disruptive. When we talk about suspension bridges, you may know that there is like huge cable that is holding the whole bridge in one piece. Inside that cable is several thousand of wires together, and it's quite usual that several of those wires break every month. So the number of events is slightly higher than collapse of a whole bridge. So if you start monitoring and saying, yeah, there are more wires breaking, then actually is being broken, then it may mean something, but it will not trigger any action earlier than in a couple of years. So there will be long-term analysis of what's going on and verification. Medium-term integrity, it's about data, let's say months scale or several months, that will probably help the operator to guess what are the maintenance costs, and in case of London, to negotiate payments for managing tunnels between tunnel operator and, let's say, Transport for London, which is running or giving money from London budget. So what about attackers or risks? This is for now, but when we were doing some experiments, we realized that we were able from ZigBee networks indirectly target the backend computer. So imagine that you can use ZigBee to propagate your data from place where you are to somewhere on the other side of the earth. So, well, terrorists, not really. They can direct tunnels and bridges directly. Competitors, not likely, at least today. So it's more about curious hackers and people like me. Well, yeah, hackers. So risks of attacks are not amplified by using sensor networks. It may be different for water pipes when you've got actuators in the network, so the network will automatically trigger some actions. And we've seen some demonstrations what can slight change in the pressure do with large water pipes. And also, it's quite easy to get through a padlock that is protecting anchorage room, you will see later on. So classes of attacks, 3 basic classes: remote, vicinity, so you're very close to the network, and physical attacks when you're physically touching the modes of the virus network. Physical attacks are difficult to do. Becher, Benenson, Dorzaev in 2006 had a paper showing that it takes a certain level of expertise and time to extract data, let's say cryptographic keys from modes and stuff like that. But what about just connecting to modes connector? I will have a slide later on. So you don't need to change anything on the mode, you just want to connect to it directly, and that's all you want to do. So I'm not going to talk about remote attacks, although the gateway is the most critical part of the whole structure. It's connected to the internet, so you can try to do remote attacks, whatever you can do with TCP over IP protocols. And you can attack it from wireless interface as well. And if you're connected via GPRS, it means that you're not going to patch your kernel every year. the gateway, if it's going to stay there 5 years, it will have the same software there. No one's going to update it, patch it over GPRS. So a bit of attacks. Let's start with code analysis. I said that Xmesh is sort of commercial extension of TinyOS. What it means is that there is part of code that you get only as compiled library. So you have to disassemble it and look at the code. There's about 15,000 assembler lines, so not that many. But you can use that, and you can use TinyOS. The code is very similar, so you can use variable names from TinyOS, and you get something like this, so something quite readable if you're really patient and you want to demonstrate something. To show particular examples, very important part of wireless networks is routing. So in TinyOS, routing is based on two metrics. It's link cost, so the cost of transferring message between two modes, and road cost transferring message between a mode and a gateway, which is sum of all link costs between the mode and the, let's say, internet. How to do it? All you need is basically a message counter that is inside each of the message you transmit wirelessly. And basically, according to the message counter, you just count how many messages you missed and how many messages you received. It's getting a bit messy with Xmesh because they just somehow decided they don't need counters in some messages, so data messages don't have counters, but well, yeah, whatever. So you can look into the code and you'll find out that when you update counters, meaning the number of missed and received messages here, you first count delta, so difference between the last sequence number you received and the actual sequence number, -1. And then somehow Xmesh did, or crossbow did this, added extra 2 lines saying that let's decrease delta by extra 1. What it means is that if you skip one message, if you miss one message, so it means if you're missing every second message, it means 50% quality of link, that it will be still 100% quality for Xmesh. And you also can see that if the difference is, it means that the received sequence number is lower than the last one you received. So sort of now the counter is decreasing for some reason. So if it is not more than 20, the difference, nothing will happen. If it's more than 20, you will forget the mode and reinitialize its table. There is some sort of routing table, so you got records for all your neighbors. Just for good measure, Xcommand feature, extra feature for Xmesh. It allows you to send direct commands from the gateway to all the modes or selected modes. No routing, only broadcast, so brute force, no optimization for power. What helps to stop rebroadcasting? Each message got message ID, and each mode keeps internal counter. All fine, so if the internal counter is larger than received message, then the message is not processed because it's sort of repetition of something that I've heard before. The problem is that the internal modes counter is not the last seen message ID, but basically a number of processed commands. So if I've seen 10 messages, and now I get message with ID 40,000, I will keep rebroadcasting and receiving messages until I do it 40,000 times. Quite handy. We were just a bit surprised why we see so many messages now for no apparent reason in the network. A bit more worried about batteries as well. So attacks. When you think about attacks, you always have to think about hardware constraints. It's about counters, size of tables, and possibly crypto information you want to add to messages. So all data structures are size limited. Not always necessarily, but that's the way. So the most interesting part is jamming, I believe. You can jam, it's wireless, no problem. The question is, can the power used by the attacker be equal to what was wasted by victim, or lower, or even much lower? Or can we even use it for some sort of smart attacks? So we did a bit of experiments with jamming using one of the modes as jammer. So the power we used was basically equal to the power used by the victim. And the numbers here is basically percentage of successfully jammed messages. So it's very close to 100% all the time, but there are some spots for no apparent reason. Engineers didn't tell us, and yeah. But it happens. The distance between receiver-transceiver was 8 meters, and the position is position of the jammer. So even jammer that was very far, far away was still very successful. So selective jamming, can we do jamming when we select which messages we want to jam and which we just let pass? And we want to do it simply and with, let's say, effective implementation. So what we did was we compiled criterion into the mode's code, we uploaded the code, and deployed the mode and let it listen. The problem is that 802.15.4 radio chips work with blocks, the whole frames. So the chip receives the whole frame, processes it, and then says microcontroller, right, you can read out the block, the frame, and vice versa. Send me the whole block, the whole frame you want to send, and I will do it for you. But fortunately, all modes got debug mode. When you switch it to debug mode, what happens is that those are 2 pins from the radio chip. So when it starts receiving message, you suddenly see clock, and you see the data bits. Right, the documentation is not precise, you have to play with it a bit, but yes, you can bit by bit read out the message and just stop wherever you want. So that's what we did. When we read out, let's say, 10 bytes of the message, we processed it. Does it meet the criteria we got? If yes, we started jamming, which took about 2 bytes to switch the radio from receiving to transmitting, and that was it. The final code quite small, about 100 lines in SC, which is C macro language. And yeah, jamming was just transmitting something random on the same channel. So we tried to jam node 24, which is down there. It was originally star topology. It sort of started behaving differently, but then stabilized into a star. When we stopped jamming, the mode 24 connected back. Protection, yes, there is some, but not very good, and it costs you energy or reliability of connections. What you can do is you can start manipulate routing tables. As I said, the whole routing is based on quality of links. You compute half of the information, the other half you get from the neighbors. So if you can fake messages from the neighbors, you can change the content of the routing table, or you can even send the whole content of routing tables into the mode. What you can do is to create sleep deprivation attack by creating a loop between 2 modes. And what happens is that when one mode sends out a message, it will be kept sending between those modes indefinitely, basically. The duty cycle can be increased from well below 1% up to 10 or 20%. So very quick use depletion of battery. I saw that you have to think about, I said you have to think about size. So one of the problems is counters. You need them all the time. So there is one counter here, 8 bits. There is another counter here, 2 bytes, 16 bits. Another one here for crypto, 2 bytes. So it's not much. 2 power 16, 64,000 messages. It's still doable. You can try to do something. So what you want to do is, well, messages are rejected if the message counter is lower or smaller than expected value. But if it's larger, by whatever value, then it's fine. There are several ways how to do it. You can inject fake messages, so the victim will forward back, so it will increase the counter. You can create a routing loop, as I said, and you can jam acknowledge frames, which will force the sending mode to replay frames several times. Or you can combine all of them. Tried, worked. Or you can think that size is everything, so the routing table size is 16. If the mode's got more than 16 neighbors, he has to forget some of them. So if you add another 16 neighbors, you basically can start sending whatever messages you want. Very briefly about traffic analysis. So this is the Anchorage room of Humber Bridge in Northern England. This is the network we deployed. Quite simple. The problem is that after 24 hours, when we looked at the topology that was during the time, you get almost complete graph. So again, if your listening is dropping on messages, then you can basically replay messages between any pair of modes, almost. What we can play with traffic, it's about topology. We can discover topology, find the most vulnerable place in the network. We can find routes to the gateway, or we can try to get data. Topology, you will use data that will never be encrypted because it has to be decrypted for the network to work. Partially encrypted data for routes to gateway discovery. Last few slides. There is TinySec, which is cryptographic library. It's quite cool. The problem is that it's only for mica 2 modes, not ZigBee modes. So if you want to use it and do any experiments, you have to port it, which we did. There is radio chip, then there is some sort of software for transmitting and receiving data. There is TinySec, again, back to the sort of communication library and then internal processing. The problem is that here, mica 2, the old modes, use 1 byte at a time, while mica that will use the whole frame. So we have to create some sort of extra layer that will cover this problem. Which was surprising because we thought, well, people are still using this sort of stuff. And on the internet, we found, yeah, we got mica that we just switched on in the makefile, crypto on, and we've got TinySec. But that's only what they thought. In fact, they had no TinySec available, and they were just communicating unencrypted, in an encrypted way. With crypto, you got 3 types of problem: implementation, computational limits, and usage errors. Problems here, which is CBC MAC, if you know, it computes messages by 8 bytes. The problem is that it starts with 0, it increments position here, but checks for 7. So the MAC is computed from 7 bytes long blocks, not 8 bytes. So it's at least incompatibility, but yeah. Fortunately, it doesn't decrease cryptographic level because they use only 4 bytes from the MAC value, so it's still fine. Hardware limits, I don't think there are any. You can use increment asymmetric crypto. You don't need it that many times. You just need to create sort of trust between 2 modes at the beginning, then establish symmetric keys. And symmetric ciphers are very efficient today. Yeah. So TinySec is excellent because it's transparent for gateway. Gateway doesn't see whether TinySec is on and off. Why? Because it works only over a wireless interface, over the air. The RS234 connector transmits everything unencrypted. So what can happen when you are able to connect to one of the modes of the network that is using TinySec, you can send messages to the mode via RS234, 232, and the mode will just send it on your behalf encrypted. You don't need to extract any keys. You don't need to mess up with the code. It will basically work as sort of oracle and will encrypt, decrypt all the traffic. So for the end, we talked to Crossbow, which is the vendor of the software. And there are points where our customers are universities and they want to play and they, well, yeah, that's what they want to do, research. And we agree that there are some security issues with the stuff we are selling and it should be solved. However, we are not interested in security until we have real customers. So yes, we don't have customers yet, but once we start having them, they will already have some solution systems in place. So when we start changing the code, they will have problems to change new code. And yeah, my time is up. I would have, yeah. No, I think I skipped that one. I got a small video about how to create loop in the network, so it really works, but yeah, it's about extra 10 minutes or so. But okay. If you got any questions meantime.
It all depends on the questions. We got usually 15 minutes, so if you want to see the video, we can just use 10 of them or something. It's your call. Yes? No. Question? Where? Okay. Are there any questions? Otherwise, we go for the video. Good call. So, hands up. Anyone? No one? Strange. Okay, go for the video then.
So, what you're going to see is there is a small network of 3 nodes, and we create a loop in those 3 nodes. Then there is just sniffer that is listening to the network, and there is one, and we use it to inject messages, a few messages to the network. And there is one control sniffer that is basically Stargate with our code. Yep. So let's connect to the Stargate first. Basically just demonstrates how sort of easy it is. Ward server is the sniffer on the Stargate, which will only show you that there's really a lot of traffic after a while. So this is the device for the USB programmer that we'll use as a sniffer and basically to inject a couple of messages. The tool we are using to inject messages is basically extension of Scapy. So we just added functionality that allows Scapy to communicate via serial interface. So now we try whether it works. So we try to sniff from the device on which the USB programmer is connected to. And it works. And small piece of Python code. So now you can see that how the messages are sent. This is in hundreds of seconds, so if you forget the last 2 digits, you will get seconds in time. So you can see basically the frequency of messages in the moment. And what we are going to do is to create 3 messages, M1, M2, M3, and we are just telling the modes that your parent is that one, and we'll create by that way the loop in the network. So we say number 2, your parent is 3, 3, your parent is 4, and 4, your parent is 2. And in theory, they should start sending messages in between themselves. So let's send all 3 messages to the modes. And you got it twice. That's it. This is basically sort of routing table or structure of the network. The higher the number, the better quality of link. Okay. Okay, message is sent. And now every dot here is one message transmitted by the modes. So there are not many there. It should be like every 3 seconds or so one. And now we are waiting only for the modes to update their routing tables after they've injected the new information for the routing tables. And here we go. So you can see every dot is one message. So it's like 40 messages per line. And within a second, you get like several hundred messages sent by the modes. And they will basically keep sending the messages for several minutes at least until it's broken by network management messages they have to send. So yeah, that's how to create loop and how to do power deprivation attack. So is there any questions now? No. Well, good for me. Bad for you. Thank you.